Any questions? How was the homework assignment for today? I didn't, I mean, I glanced over it, but I didn't do it yet. Is there any questions on it? The other two homework assignments are on the video, which is up on Media Gallery, but we did do those last class. Share. Okay, it was a number, oops, number 37. It says atmospheric carbon dioxide combines with rainwater to form carbonic acid that can dissolve surface rock. This rock weathering process transports raw materials for shell building marine organisms in the ocean. Therefore, sedimentation, these shells eventually become limestone. This process of chemical weathering and biosequestration, which takes place for hundreds of thousands of years, is depicted in the stock flow diagram on the next page. An increase in temperature tends to accelerate this process. Label the flow arrows and control arrows with the appropriate positive or negative sign, and identify the feedback loops as amplifying or stabilizing. So we want to add and subtract, and it says an increase in temperature accelerates the process. Figure 43, 41, 42, 43. Okay, so if we look at this one, we have the temperature. Let me write this out real quick so then I can write on it. But do the blue arrows. Remember the blue arrows, if they are going into your stock, they're a plus. And if they are leaving the stock, they're a minus. The stock is the square. So this one has three different stock: the CO2 in the atmosphere, the limestone, and the global temperature.
That derivative negative, right? Good.
Okay. So the first thing you want to do, the blue lines are these. Now, it's weird that they're starting, this is a stock. This is leaving the stock, so this one's a minus. This one's going into the stock, so it's increasing the limestone. I think these both had spigots on them. This one is going into a stock, so it's increasing it. And this is coming out of the stock, so it's decreasing. So you always want to look at your stocks first. That's the square ones. And if it's leaving, then it's a minus. I mean, yeah. This one's going into a stock, so it's a plus. This is the first, I think, that we've looked at two stocks in the same group. Now they told us as global temperature increases, this increases. So as this increases, this one increases, that's a plus. If as the temperature got hotter, this decreased, then it would be a minus. So you're always starting where your arrow is beginning, and then it's going to go to. The part you're starting at always is increasing. And then see what this one will do. If the temperature goes up, this goes up. It was the last sentence I had read. An increase in temperature tends to accelerate the process. And so that's why that pink arrow is positive. Right here. Now, if CO2 increases, then long wave radiation increases because CO2, I believe it increases them. It's part of the long-term carbon cycle. Okay, so what's happening? I thought so after I said that. I wanted to double check. But as CO2 increases, you have less long waves, because remember, those are the ones that are going out and the heat is leaving, but we're holding it in, so there's less of them. So on this one, as there's more CO2, there's less long waves because it's holding it in, it's blocking it from leaving. So this one is a minus. Any questions on those?
I hate how the book only shows like one page at a time.
Yeah, I agree. And they should have explained this more, but I guess they assumed because we learned it in the other parts, but I just wanted to double check. Yeah. And I wish they would have put it on the same page instead of putting those graphs separately for all of them. But the global temperature increases, this increases. If CO2 increases, then it's holding in the heat and we don't have the long wave radiation. Now, if we look at different loops, let's see, it did say to find the feedback loops. One could be this one. And if we go from atmosphere to here, down. That loop has 1, 2, 3 negatives. So this feedback loop has 3 negatives, which would odd stabilize. This one doesn't, they didn't have this connecting to anything, so this does not have a loop. This is the only loop. Yeah. Because anywhere else it's going to end, it's not going to loop. So there's only one loop. And there's 3 negatives, so it's stabilizing. Any questions on that? The next one has to do with what we're learning this part. I have a meeting in what, like 20 minutes. So I don't know if I want to just have you read it and then we'll do it on Friday. Let me show you the graphing part though. But is there any questions on this? Open desmos.com. Now there's the formula we're going to learn. It's your starting amount, R is your rate, and then N is the number of times it's compounded. But for what I want you to see is just the graph right now. We'll get to this next class, but this is the formula I'm using. This one's confusing. I'm going to show you how they use that, but this one's better. So if we look at S sub n equals S sub 0, 1 plus R to the n. R is the rate as a decimal. S sub 0 is the starting amount. And this works for anything. You can use it for bacteria. Right now, we're going to use it for finance. Like if you put so much money into an account. So if we look at this problem, we're investing $100. That's our starting amount. And we want to look at these different interest rates and see how it's going to change it. Because these little changes, when you're talking about later, many years later, grow a lot faster than the other, even though the percentages are not that big. And so it's showing you when certain things are growing fast, like the trash in the ocean, these little percentages of differences make a huge difference in the future. And so if we look at this, and in place of R, we want to put each of these rates just to see what happens. Now for the window, I want to use this. That way then you can see it. So first we're going to do the window. To make a window, click on the wrench. Now you don't have to, if you were doing this and you're just checking problems, you can hit the plus and the minus and it'll zoom in and out. But I want you to see an exact portion. So X goes 0 to 20. So right here where X is, go 0 to 20. And Y 0 to 500. Now for the equation, we're going to use Y equals 100, 1 plus, and then R at 2% as a decimal 0.02 to the X. And we want to see what that graph does. So if we look at 100, we'll put Y equals 100, 1 plus 0.02. And there's our graph. Now what we can do is we want to change this 2 to a 4 to see 4%. Now you can highlight it and click Control C and then go down here and hit Control V. That way you don't have to retype everything, and then just change your 2 to a 4. Now it starts at the same, but then it grows a lot faster. So what I did was I highlighted it and then clicked down Control C and then Control V, and it copies it. And then I want to change my 2 to a 6. So that change in that percent, 2, 4, 6, and 8, it grows so much faster. And if we went further than the 20, I changed it to 40, you can definitely see how much faster the 8 is growing than the others. So exponential growth may stay close at first, but then it gets, as X is getting large, and this is only 30 right here. It's gotten so much larger. Any questions on that? So this is your rate, and this is your total compounding. By total compounding, let's say we had the $100 in there at 2% compounded monthly. For 4 years. To find, it's now an X, but the formula is an N. But to find that value there, because we're putting the $100 at 2%, X is the total compounding. What that means, I spelled that wrong. It's how often, so monthly would be 12 times, and how many years. So it's the number of compoundings in 1 year times the number of years. So we have $100 put into an account at 2% compounded monthly. If we plug 48 in for X, that will tell us how much will be there in 4 years if we don't touch it. It just sits there. Plug that in. You should get, I got $258 and 70, if we round to the nearest penny, 71 cents. Any questions on that? So the N in the formula I had showed you is the total compounding. You could take compounding in 1 year and multiply by the number of years. And that will give you your N. Any questions on that? So this section talks about, it's called exponential growth because it's growing exponentially. They'll also talk about exponential decay. The one graph we had looked at, oh, I know, it was the bathtub. Even though this is growing, it's an exponential decay. It's growing a lot faster at first, but then how fast it's growing is slowing down. And because that increase is decreasing, they call it a decay. So when we look at this one later on Friday, this, even though it looks like an increase, it's growing slower each time. So if we went by minutes, and I think it said this is 55 minutes. Each additional minute, it's growing a little bit less than it did the minute before. So that's called a decay, because how fast it is increasing is decreasing. Does that make sense? Where this one is just increasing by a larger amount every single time, kind of like doubling. Where this one, yes, it's growing, but it's not, it's decreasing how much it grows by until it staples off. So this is an exponential decay. These are exponential growth. Any questions on that? Okay, so for Friday, read through 3.4. I think what I gave you should help you understand it more, but that way then you've looked through it, and when I explain it, I think it'll be easier. We will still go through the whole thing, but read through it so you understand the wording and things like that. Unfortunately, I have to go to a meeting, so I have to cut it short today. But are there any questions? I think we will cover what I put on Friday. If not, at the end of class on Friday, we'll do it. Or if I don't think you're ready for it, I'll move it to Monday and we won't worry about Friday. But I think we'll cover everything and we'll just do it at the end of class on Friday. Any questions? Okay. I will see you on Friday. My office hours, if you needed to come today because of this meeting, they won't start until 11:30, but I'll be in there by 11:30. Have a nice day.